All right, so I'm going to make a quick video before lunch. So this is for all of my Math 12 classes out there. Here we're going to do from Chapter 7, Section 3, we're going to do another example on forming a confidence interval for uh, the true proportion of the population that do whatever, whatever the thing of interest to the researcher is. All right, so in example 7-10, about self-driving cars. Okay, so the future's getting here. Let's see. A survey of 6,000 adults, right, found that 58% say they would take a ride in a fully self-driving car. Oh yeah, count me in. Find the 90% confidence interval of the true proportion who said that they would take a ride in a self-driving car. All right. Okay, so let's get right into this. Okay, so here it is. It is, hang on one second. Let me adjust a little bit. All right, it is example 7-10. Can't remember the page number, but I'll let you go ahead and look that up. N is given to us as 6,000. The survey was of 6,000 people. And notice here, we already have p hat is 58%. So 100% minus 58%, that gives us 42% for Q hat. All right, so that basically was almost entirely it. The only other thing that we should kind of probably check for in each one of these is that we satisfy the conditions that we have what n times p hat greater than or equal to 5, and also at the same time n times q hat is greater than or equal to 5. So what does that mean? In other words, we need to have a sample size sufficient such that we have at least 5 successes and at least 5 failures. If we don't have that, no matter how large our sample is, the the results are not going to be accurate. All right, so here, in order to use these results, the formula, we have to have that condition in place. And here, let's see, I have no idea what 58% of 6,000 is. I know it's more than half, and let's see, that's more than 5. All right, again here, that's not quite half, but it's at least, 10%. 10% would be 600, so that's bigger than 5. All right, so that part we didn't have to worry about too much, but it's always good to check because sometimes you can't make an assumption in the middle of a problem, or else you don't get to use those techniques that you're normally used to using if you don't have all of those conditions being met. All right, so Grenfell, stop stalling and actually get to the problem. All right, so we're going to compute the margin of error is going to be z subscript alpha over 2 times, normally we would write what, sigma, or sigma divided by the square root of n for our standard error. Here it is p hat times q hat. We don't need to put the dot. All divided by n. That n is underneath the square roots. Make sure that's in there. Okay, so let's go ahead and plug in all of that stuff. Oh, I'm sorry. The first thing that we need to do, one of the things that we need to do, is we need to find our critical z values. So here's our distribution curve, roughly. All right. We were given that we want the 90% confidence interval, I believe. Okay, so alpha would be equal to 10%. And so that means that alpha divided by 2 is going to be 5%. This is looking rather familiar, but that's probably just because this is such a common type of question. And there's only so many percentage levels, I'm sorry, or confidence levels that we have for these confidence intervals. 90, 95, 99, those are all really standard. And so we're going to keep coming back to, the same values for alpha and alpha over 2. And since we're using the z distribution most of the time, right, this doesn't apply if we have to use the t distribution, if the population standard deviation is unknown. Okay, we'll keep coming back to these very familiar values for z subscript alpha over 2 and negative z subscript alpha over 2. Our critical z values are going to be very frequent ones, right? In fact, I'm just going to show off, and I remember this one is negative 1.65, right? Let's just pause and double check. Let's see, negative 1.6, if you can see that, slide over to 5, and there it is. Yeah, remember that was one that was right in between negative 1.64 and negative 1.65, so we had to round it. Okay, so there is our critical z value. Remember, we don't put the minus sign in there, even though we're finding that left area first. It's on the left side of the graph, so it's going to be a negative z value, the thing that we actually find. All right, for the square root portion of this, we're going to have 0.58 times 0.42, all divided by 6,000, and all of that is happening inside the square root. Okay, so now I will have to pause to grab the calculator. Let's go, calculator. Okay, so I got the calculator out and I just punched everything in. And so here we get 0.0105. We'll just cut it off there, round it off. Okay. Now, just one thing about this. In the past portion of what we've been doing here, our margin of error has been well, I don't know. Here, I'll put it this way. Sometimes when I'm looking at a result like this, a lot of the time, in fact, and here I'm trying to encourage you to adopt this behavior. I describe it as, like my spidey senses start tingling. And something about this problem, it struck me when I first got this out of my calculator, is wait just a second. This is it supposed to be this low of a value? I mean, what's the deal there? And then think to myself, okay, well that makes sense. In the past couple of sections, when we've been trying to find the confidence interval for a mean, usually the margin of error is some larger value. Why is it small here, and why are we okay with that here? Well, here's why. It's because this is the margin of error for a proportion. Remember, a proportion is a percent, and so saying our margin of error is plus or minus 1%, that's actually really reasonable. So remember, 1% as a decimal is going to be 0.01. So as a numerical value, it's going to look pretty small. Okay, but here it should be all right. So remember, P, the true proportion, is going to be, I'll write it just like P hat plus or minus E. Okay, and so remember, that means P is in between, well, on the one hand, we're going to take 0.58 plus 1.05%. Okay, so that'll give us 0.5905. All right. And then on the other hand, we're going to subtract away 1.05%. So that's going to be 0.5695, I want to say. Okay. You might want to double check me with the calculator on that, because I've been known to do my mental math wrong. In fact, you know what? I'm just going to go ahead and check it with the calculator. Let's go ahead and turn that back on. Plus, right, so we go 0.58 minus 0.0105. And, oh yeah, good. All right, tripping out for no reason. All right, so that is our 90% confidence interval for the true value of the proportion. So again, just to reiterate, what is a confidence interval? It's an estimate, okay? So we're estimating that the true proportion is somewhere in this range. Is it guaranteed? No. only 90% of the time. 10% of the time, it might be outside of the range. Okay. Let's see, exactly 5% of the time, to be precise, it's going to be above 59.05%, and 5% of the time it's going to be below 56.95%, right? But 90% of the time it's going to be in this range, right? Why do we want a confidence interval? Just one last little blurb about this before I sign off. Well, um, an interval estimate versus a point estimate. If we were just going to say, here's a point estimate, you know, the population, is 58%. There it is. That's our final answer. Well, you know what? That's wrong 100% of the time, because even if the true population proportion is 0.580001, it's not exactly equal to 0.58, so it's not that value itself. So if we put down a range of values and we're saying, as long as that's pretty small, yet it happens a significant portion of the time, remember that's the significant level of our confidence interval, right? Then that is going to be a better estimate, because that gives us a higher likelihood of actually getting that accurate value for our whole population. All right, so we'll finish off there, and then we'll talk about the relation between the uh, sample size and the margin of error. Okay, signing off.